My name is Daniel, and we're going to talk about energy anonymity networks in smartphones. So if any of these words sounds interesting to you, you're hopefully in the right place. And at the end of the talk, I hope you take 4 things away. That cryptography on smartphones is relatively cheap. The patterns of radio transmissions matter a lot. Tor and VPN are quite feasible, but covered traffic can be expensive. And we're going to walk through all these in the talk. But well, what's our motivation? Why are we interested in this? We found that way too often we assume stationary computers when we talk about anonymity networks. There's the famous plug in the wall that gives us unlimited energy, and we always have reliable and fast connectivity. And the giveaway is usually somewhere in the evaluation section where it says, oh, we tested the system on some AWS EC2 instances. However, smartphones become like the primary computing device for many of us, and for many, it's the only computing device they own. And it comes with 2 important challenges. One is the connectivity is often sporadic, so the device might be offline, the bandwidth is lower, latency is higher, and there's limited energy supply. We have 1 battery that needs to get us through the entire day, and that's a problem we are focusing on in our work. So what we do is we actually measure the power. So we put a power sensor between the battery and the smartphone, and then we have an Arduino who logs the data to the computer. And all of this is open hardware. So in our GitHub, you find some assembly instructions, all the 3D prints, and the software. So if you have 1 or 2 afternoons to spare, you can build the set yourself. And we also went, of course, through the artifact evaluation process. And when we talk about the power and energy, what we use is a metric where we invented. It's called battery percentage points. It's a bit more intuitive than talking about joules and milliwatts. And the idea is if you start with a full battery and after 12 hours you had 40%, then you used 60 percentage points of energy, or about 5 percentage points per hour on power consumption. And that hopefully is a bit more intuitive to understand what that means for the user at the end of the day. If we want to just measure a protocol run, something that runs in the background, then that's quite easy. We just start the protocol, start our measurement, stop the measurement, stop the protocol. The timing of the start and stop is not really interesting here because we are interested in the average power consumption. So that's pretty straightforward. But sometimes we also want to measure short individual operations. So we want to know, okay, this one cryptographic operation, how much energy does it actually take? And what we do for that is we add a little USB to serial device to the smartphone. And before we start our measurement, we use that to synchronize the clocks so that then when we run the operations, we remember the timestamps before we start and after we stop. And then we can later overlay that at our measurements data and extract the portions where the individual operations take place. And to give you a bit of an illustration, so this is a quite expensive operation on smartphones, generating a long RSA keys. And what you see, it takes about like 3 seconds. In the beginning, the power consumption goes up a bit. That's the CPU increasing the clock as there's quite a lot of work to do. And what you hopefully also take away from this is for like any computational task, runtime is a good linear proxy metric to the overall energy consumption. And if we compare this, for instance, with elliptic curve, the key generation there is way more deterministic and way faster. And actually, what I showed you with the RSA key generation, it's a bit of an outlier. It's by far the most expensive thing we can do. And that costs around 0.01 percentage points. So we can only do like 10,000 of those on the battery charge, whereas knock yourself out with elliptic curve cryptography, you can do millions of those during the day. So that shouldn't be any problem in our protocols, and that's the first takeaway. It's, of course, way more details in the papers if you're interested. So that was all nice and linear and simple, but radio communication patterns are way more interesting because they have a lot more subtlety to them. This is a power trace when sending, receiving some data over 4G, and you can already see the y-axis go up to like 40 percentage points per hour. So we're using a lot of energy from the battery. And what happens is, in the beginning, the smartphone reaches out to the cell tower, negotiates the connection. So that's a state transition that costs some energy. And then we do the actual work. We send some data, we receive some data. So you see that is at receiving quite a lot of power consumption. But then we have this odd bit that just happens after we actually close the socket. That's the tail latency. And that's because the underlying layers don't know if our application wants to send or receive more data. So they have a guess, and they wait for a bit before they finally disconnect. And this tail latency is very interesting for us, because you might see that when we, for instance, send a single byte every 6 seconds, then that's quite literally the worst case and the most inefficient way we could do this. And we pick this up later when we talk about cover traffic. And to make things even worse, this is kind of a black box. So there's no API to figure out this. It's different between smartphones, different between network operators. So radio transmission patterns matter. But let's look at some anonymity networks that are in use today. And for this, we first look at two simple variants like VPN and Tor. And we have 2 scenarios: an idle scenario where we don't do anything, we just let it run in the background. And then we have a web scenario where we load a website every minute. And VPNs are quite feasible. So the overhead when the device is idle is less than a percentage point. And especially on Wi-Fi, it's very negligible. If we do some data transmissions, we're using up to 1 percentage point per hour, but only in our construed example where we actually do quite substantial work every minute. The other good news is Tor is just as good as VPNs in idle mode. The phone just goes in its low power state when we're not doing anything. So that's quite feasible. We see a bit more power consumption when we do work, and that's just because the latency and is higher and the bandwidth is lower when we're using Tor. However, Tor also has a feature that's called connection padding, where the guard nodes and the client send some packets to keep the connection alive, make it a bit harder to determine when it starts and stops, and that comes with some significant overhead. So overall, we think both are feasible, and we pick this up later when we talk about our general validation study we also do. However, VPNs and Tor both suffer from being vulnerable to traffic analysis. If someone observes the traffic patterns and the message sizes, then they might conclude in this example, without even looking into the anonymity network, that A is sending some data to C, just because the message patterns align well, and if they can do this multiple times, they can build up their confidence. And the general technique we use against this is cover traffic. So we encrypt and pad all messages to the same size and send them independent of our actual communication behavior. So we have all these cover messages lined up, send them, for instance, every 5 seconds. And if we actually have some payload to send, we replace the next cover message with a payload message. The question now is, what numbers do we pick? And if you remember the power trace of the radio transmissions, something like 5 seconds or 6 seconds might not be the ideal thing here. In fact, what we did is we looked at quite a lot of different parameters and also at different payload sizes. We have 4G and Wi-Fi, and what you see, Wi-Fi is way more green because it has less cost for the state changes. And for 4G, really only very low rates are feasible, whereas everything that's low latency uses up a lot of battery power. And interestingly, if you look at one of the diagonals, these are all sending 100 kilobytes per second. But if we just increase the delays between the packets, we can send the same throughput at much lower power consumption. So cover traffic can be actually quite expensive, and that's something we should take into consideration when designing the protocols. And finally, what we did is we tried to simulate a typical day where the smartphone connects to Wi-Fi and 4G, and every 2 hours we simulate some active device usage. So in this chart, you see the like a burn-down chart of the battery charge. We're starting 100%. The gray areas are connection to 4G, and the white areas are connection to Wi-Fi. And wherever you see the big drop, that's where we actually use the smartphone actively for 10 minutes. So the blue one, that's our base scenario without any anonymity network. And then both VPN and Tor come with less than like 5 percentage points difference at the end of the day, which is really good. Also, kudos to the Tor and Orbit developers. They're actually performing better than the VPN client in our tests. So that's some indication for good engineering practices there. However, if we take a protocol like Loopix, which uses cover traffic, then we see quite a different picture. So the line with the big pink arrows on it, that is a configuration that's used by NIM, which is a Loopix implementation. And we can also see the slope when it goes into the 4G area, when we actually use the mobile network, that gets really steep. We use a lot of energy. We burn through all that power quite quickly. So looking a bit of the limitations of our work. So this is really a glance at the problem. It's a first step. So we only look at one Android device. We only look at one network operator. The scenarios are arguably quite simple. And we also look only at part of the configuration space, especially for VPN clients. There are tons of options to explore, and they probably can perform way better than what we have been able to measure here. And that also means there is a lot of interesting work to be done. We think this is a very nice and interesting area in the trade-off space, trading anonymity for energy and the other way around. So we can probably do much better when we have more adaptable designs that take hardware constraints into consideration. And we hope our work and also the prototype motivates others to do a bit more of the measurements of the energy consumption, take smartphones as a primary computing device for what we develop for, and we're of course very happy to collaborate on this. And before I come to a close, just want to say a big special thank you to our reviewers and shepherds. So we went through the major revision, and we found this was actually a really great experience. We had a lot of really good insights from the discussions, and it made the paper much stronger as a result. So that was really, really great. And so I hope if you have any questions, either ask a no or send us an email, read our paper, and check out the artifacts. And thank you very much.